And then what we're going to do when we start talking about polar coordinates, we're going to apply everything that we know about parametric equations to polar coordinates, because polar coordinates really are a set of parametric equations. So we're developing the tools with parametric equations that will work with any type of parametric equations. And then when we talk about polar coordinates, we're going to talk about a specific kind of parametric equations. All right, so on Friday, we came up with the arc length. If x is f of t, so we have a pair of parametric equations, y equals g of t. We came up with the arc length is the integral from a to b of the square root of df dt squared plus dg dt squared dt. That was our arc length. And we want our curve not to intersect itself anywhere except at the endpoints on our interval of integration. If it does intersect itself more than once, then we have to break up the integral into multiple pieces. And we could shorthand this a couple of ways. Integral from a to b, often you'll just see this written as f prime squared plus g prime squared dt. And then sometimes we shorten it even more, and we call this entire thing the square root of f prime squared g prime squared dt. We just call that ds, the arc length increment. So we'll use this more later, we would say ds, where ds equals this whole quantity.
Wait, ds equals 2?
No, this quantity, the integrand, is ds. The arc length, we think of that as a little tiny piece of arc length, and we're integrating the arc length over the interval. All right, so I just want to go through an example. As you might expect, with these square roots and the derivatives squared, you get some possibly interesting integrals. But when we represent curves with a set of parametric equations, often we can find information about the curve that would be almost impossible to do with rectangular coordinates if we had an explicit relationship between y and x. So, for example, we want to find the length of x equals cosine cubed t and y equals sine cubed t from 0 less than or equal to t less than or equal to 2 pi. So for an explicit relationship here between x and y, it's not simple. Any guesses as to what this curve is? This is an asteroid. It looks like an asteroid looks like this. It should be symmetrical, but it looks something like that. And this is 1, 1, negative 1, negative 1. All right, so what I want to do here is just find the length of the curve. It's symmetrical, even though my drawing is not symmetrical. We're going to find the first quadrant portion and multiply by 4.
Oh, yeah, I remember this. Oh, yeah.
So we could do the entire integral. It's not doesn't make that much difference. I just just going to do the first quadrant. It's symmetrical, so we can do the first quadrant multiplied by 4. Dx dt squared is 3 cosine squared t times negative sine t squared. So we get 9 cosine to the 4th t sine squared t. Dy dt squared is 3 sine squared t times cosine t squared. 9 sine to the 4th t cosine squared t. And then the square root of dx dt squared plus dy dt squared. This is going to be nice. Is the square root of this entire quantity, the sum of those two things. So what are we going to do with that? That looks really messy.
Factor out.
Factor out.
Let's factor something.
Shut up.
So I'm going to factor out. We have a common factor of sine squared plus cosine squared.
Sine squared, cosine squared.
And this can be times 1 because it's cosine squared.
And then we have a 9
Okay.
cosine to the 4th.
Kevin, you're a genius.
Sorry, cosine squared t sine squared t. Well, that looks a little better, huh? So we just get, this is 1. We can take the square root of that, and we just get 3 absolute value of cosine t sine t. Square root of something squared is the absolute value. And in the first quadrant, since I'm talking about the first quadrant, these are going to be positive. But this is going to be positive, so I'm going to say 3 cosine t sine t for 0 less than or equal to t less than or equal to pi over 2. So I don't have to worry about that absolute value in the first quadrant. All right, so that's not a bad integral. So I'm going to say our arc length s equals the integral from 0 to pi over 2 of 3 cosine t sine t dt. Nice, easy u sub. You can pick either one of the quantities to be your u. I picked sine. So this is going to be what do we get? Oh, I need a 4 here. So I get a 12 sine squared t over 2 on 0 to pi over 2. And what does it come out to be? Someone said it. 6. Was that a guess?
I just said it was 12. But I knew. No, I knew.
You knew. Yeah, good.
I knew. I was right there. I was 6 steps ahead.
Because the sine squared of pi over 2 is
Right. Yeah. of
0
course.
and sine of 0 is 1.
Well done.
Yeah, that was a quick
Just a little too.
quick integral evaluation, Connor. That's impressive.
Yeah. Honestly.
You're an integral prodigy.
Really badly. Wow. I got you bad. Wow. You jumped like really high.
I just shot.
The what?
Just the original. Okay, so I wrote it down right.
All right. So often the integrals that you're going to evaluate require some manipulation for them to be doable. All right, let's look at areas of surfaces of revolution.
That's easy.
So our surfaces of revolution, we're just going to apply exactly the thinking that we applied to surfaces of revolution before. We have our arc length, little piece of arc length. We're envisioning these surfaces as being small portions of frustums of cones, and we're adding those up. So we're going to say our curve is smooth. X is f of t. Y is g of t. Doesn't cross itself. On our interval of integration. Doesn't cross itself. So our surface area. I'm going to say 1, big S here, is 2 pi, because we're revolving this. The 2 pi is our, gives us our, since we're talking about frustums of cones, we can have little pieces of circles. The integral from A to B, we need our radius of revolution. Well, if we're revolving about the x-axis, our radius of revolution is y, so we just have g of t times our arc length.
Can we just say ds?
If you would like to. dt, just as long as you remember what ds is.
She's gonna
And this is
It's just the given. He's gonna forget.
revolution about the x-axis. And we need g of t, our radius, to be positive. Or non-negative, I guess. Because it can be 0, we just don't want it to be negative. And if we revolve about the y-axis, we get 2 pi a to b. Our radius is then just x. And this is revolution about the y-axis. And we need our radius f of t non-negative. So the nice thing about, one of the nice things about representing curves in terms of parametric equations is we don't have to worry about solving for x in terms of y. We don't have to worry about how our function is set up to revolve about a different axis. We just use a different radius. Yeah, it's nice. All right, so let's look at an example, a nice example involving these ideas. And again, you could represent this if you would like as ds. So this would be 2 pi integral of gt ds. 2 pi integral f of t ds. We want to find the surface area of x equals cosine t, y equals 1 plus sine t, from 0 less than or equal to t less than or equal to 2 pi, revolved about the x-axis. Before we set this up, any ideas what this curve is? Circle?
It's a circle that's been
I don't know why you guys are laughing. Should I go? It's accentuate.
Well, so if I were to if I were to eliminate the parameter, for this portion, I would have to say y minus 1 equals sine theta. And then x squared plus y minus 1 squared equals 1. So it's shifted up 1. So it's a circle shifted up 1. So what we're finding is the surface area of kind of a torus, a donut shape. So we're revolving that circle, shifted up 1. We're revolving it about the x-axis. What's that? We were just, I was just eliminating the parameter so we could just have an idea of what this is. We don't need to do the problem. This is the standard parameterization.
Oh, those are big words.
Of a circle with a center 0, 1, with a radius 1. So we will, especially next semester, not so much this semester, but next semester we will get very familiar with these various standard parameterizations, and you'll look at that and say, oh, that's a circle, shifted up 1. All right, so about the x-axis, our radius of revolution is the y quantity. So our surface area is going to be the integral from 0 to 2 pi of, I'm going to say 2 pi times y, 1 plus sine t, times the square root of dx dt squared minus sine t squared plus dy dt squared cosine t squared dt. That's pretty nice, right? That's just 1. So we have 2 pi integral from 0 to 2 pi of 1 plus sine t. And, oops, dt. Easy integral to evaluate. Be careful with these, with your signs, because sines and cosines do have values, some of them, at 0. So it's easy to say, oh, at 0 that's 0, but sine of 0 is 0, but cosine of 0 is not 0. So be careful with those, the plus and minus signs when you evaluate this. We get 4 pi squared.
Which is close to 5.
Yeah.
Really?
Or, yeah.
4 times 3 squared.
Yeah. Hey,
It's close to a multiple of 5.
there.
There you go.
Can anybody think of a different way we could find this area?
Not do it.
How about the theorem of Pappus?
Oh,
I don't remember.
Oh, that was for volume though, wasn't it? That was for volume. I'm wondering though if it would, if we could, yeah, we might be able to do something like that with the surface area, maybe. Yes, theorem of Pappus was for volume. But we got a similar, we get pi squareds with the theorem of Pappus as well. All right. The theorem of Sam, is there a theorem of Sam? That's like several years ago we had Seth's law. Thank goodness that's gone.
Wait, what was?
I'm not. I promised Miss Hine I wouldn't ever repeat it.
Wait, please.
All right.
I don't know what it was.
It becomes a thing. It becomes a thing, and it's a very annoying thing.
We have the Xylee theorem where if the talk goes faster than the bottom, kind of cringy.
You don't have to do the
If we get-
problem.
They're all that to make it. If we replace them as Xylee theorem.
Oh, the Wiley.
But and Jack found a elegant proof for the theorem, but the margin of his paper was too narrow to contain it.
Exactly.
The theorem grew larger faster than the area of the margin of your paper.
So this is basically just a formula that we we have to write down on our note card is use.
And remember how to use it correctly.